So a few years ago, I went through a couple bouts of headaches. Some were rather severe. I had like what they would call a thunderclap headache, just spreading from here, boom, all the way through my head, and then later just constant and headaches that were roughly in the same region of the head. So the first time I actually was put into an MRI scanner to make sure that there was nothing scary going on. Thorough doctors wanted to rule out things like blood clots and tumors and lupus.
So it's not a typical case. It's not lupus.
But after the first amounts of treatment, they basically said can't do anything, and then the headaches largely went away. A few years later, they came back, and they ended up being kind of persistent. Ow. So I ended up getting a CT with contrast afterwards. Both of the MRI and the CT scanners allow you to get a 3D image of what's going on inside of somebody's head, or their leg, or wherever else you put in there. Actually, from what I understand, a lot of vegetables get scanned in CT scanners and MRIs because when technicians need to try something out, that's what they have on hand. Ultimately, doctors decided that I had nothing severe wrong with me, and they just told me I had non-specific migraines. So I have been largely headache-free for the past couple of years, but they do come back here and there. So now, why don't we talk about what actually goes on with a CT scanner and MRI? If you took my class last semester in tomography, or followed me on YouTube, then you'll have a good idea of how it goes down. I went through a full breakdown of the radon transform, which comes up in CT scanners, and how to invert the radon transform using Fourier methods. But there are other methods like algebraic methods, which I touched on, but we didn't go into much detail. This gives me an opportunity to go into a little bit more detail here. So what's the data that you get from CT scanners? This is a data science class. The idea is that you have a scanner, and there's a X-ray machine that is sort of going around in a circle, and it fires an X-ray beam through a subject. Now on the other side has a receiver that will say what the intensity of the beam is when it arrives there. You can determine if there was an object in the way basically by just looking at how much of the X-ray was absorbed. This corresponds to what is called Beer's law, where as an X-ray beam travels through a substance, you can sort of think of it as sort of each little piece having sort of an infinitesimal absorption, and then that accumulates through an interval. And this is what gives you the radon transform. The radon transform can be seen as the integral of all the absorptions through a subject in one direction, so in a straight line. Then what the CT scanner does is it moves the X-ray machine, and then it takes another X-ray in a different direction. And once you have enough directions, you can actually tease apart the different infinitesimal absorption areas, and you can rebuild the inside of your subject. So this is how CT scanners work, and this led to a Nobel Prize back in, I think, 1970s. I think it was like 70s. I made another video on that before, but I'll put it up here too. Then MRIs worked on more or less the same principle. They don't fire X-rays, but they do take images from a whole lot of different directions and reconstruct them to get the 3D image on the inside. I might make a video on that later. I did promise my last class I would do that at some point. So the first couple methods for analyzing X-ray beams used what is called Caspars Method, which was basically treats the subject as a collection of pixels. And basically the idea is that you collect a whole bunch of information if you treat each of these pixels as a different basis function, and then you say, over this square, I saw that the X-ray beam must have traveled through it, and then you can say, well, it traveled through this square, this square, this square, and this square, and so then the X-ray beam must be the accumulation of however much absorption this particular square had. So it sort of discretizes your brain or other parts of your body into these sort of infinitesimal absorption squares, and then If you make a grid of that, so you have 256 by 256 as your sort of subject area, or larger in modern machines, basically you can treat it as a linear problem. You have all the weights that must be attached to each of these squares, and these weights correspond to the amount of absorption that happens in there. How do you determine what each individual weight was, even if it is in the way of other ones? Well, basically you just have to pick enough independent directions that you can get enough of a rank out of your linear system in order to solve the problem. There's a bunch of ways of solving this, and you can think of this in terms of what is called least squares and other things like that. The Caspars Method uses a collection of affine projections and iterates it. But today I want to talk to you about how you can use the SVD. The SVD allows you to define what is called a Moore-Penrose pseudo-inverse. So we know that your ultimate linear system is going to be the matrix, which has all of the lines and directions and the integrations that must have happened through each one of the squares. Then you have the weights attached to all the squares, and then on the other side you have the actual absorptions that you detected. Now the weights themselves are going to be there's a lot less weights than there are measurements. So basically for each, direction, for each line you have coming out of the X-ray, you're going to have it in, say, 180 different directions, or hopefully fewer. You don't have that many X-rays of a person. But at the same time, you do need to have enough in order to get a good enough resolution. So again, basically take that same X-ray and rotate it 180 degrees, and then but on each X-ray, you're not having just one ray, you're having like a whole array of rays. And so then that gives you a huge number of samples and a huge matrix that is very, very tall, but rather thin. And this is multiplied by the rather short weight vectors, or relatively short weight vectors. Short could be 16,000, but it's still less than, say, the number of samples they've taken. It is equal to a very tall matrix of samples. So what you can do in order to pare this down is you can take that matrix, let's call it A, transpose it, and multiply. Now, what you end up getting then is A transpose A, which is a square matrix that is exactly the size of your weight vectors. Now, if your matrix A, which was very, very tall, but very, very thin, had the same rank as it has columns, then what that means is that A transpose A must be a square matrix that is full rank. And this goes back to the little lemma that we talked about in the theoretical portion of the SVD video. Now, what we can do now is that we have A transpose A X, let's just say X being our weights, or maybe W. A transpose A W is equal to A times B. That is our new system. A times B is now a vector that is as the same size as our weight vector, and now we can invert A transpose A with its proper inverse, because it's a full rank matrix. This gives you W is equal to the inverse of A transpose A times B. And therefore, you've teased out exactly what the weights need to be on this basis for this CT scanner. Now, what you can do is you can use the singular value decomposition in order to get an explicit description of the Moore-Penrose pseudo-inverse. So if you take A and you write it as U sigma times V star, like you usually do, and then you can go ahead and you write the pseudo-inverse of A, which we write as A plus, is equal to V times sigma plus U star. And so sigma we know is a diagonal matrix, and so in order to make sigma plus, what we do is we just go through and we take all of the singular values, take the reciprocal if they're non-zero, and if they're zero, we leave them alone. Then what we end up getting is this sort of pseudo-inverse of our sigma matrix. And we know that the SVD actually ends up being an easy thing to compute, and it always exists for any matrix. And so as long as we end up having so that gives us a sort of inverse for very tall and thin matrices. If you'd like to learn more about this, I'll put a link up here where you can get the full lecture with me breaking down exactly how to compute the pseudo-inverse using the SVD. And I'll also go through exactly how we're going to construct this matrix from these integrals and the Radon transform, and then I'll run a few examples in MATLAB showing you how you can actually implement this. Now, modern CT scanners don't usually use these algebraic techniques. They use what is called the filtered back projection, which was the focus of my last class, which covered the Fourier transform and a lot of other stuff, and you should go and check out those videos if you get a chance. Anyway, and if you're externally from my class, please go ahead and subscribe. I'll have a lot more interesting content up here on data science and dynamical systems. This ends up giving us a really nice sort of test of these methods in a situation where you can actually see the ultimate result. Okay, so I realized I never actually said goodbye. So go ahead and click the next couple of videos and you can see me in this snazzy shirt going over MATLAB examples and over the lecture. But if this is where you're signing off, take care and I'll see you next time.